Mr. Dimitrich, we've been sort of lying about gases for a little bit, and we want to kind of
Come clean.
Come clean, yeah. So we've been talking about gases, and we're making an assumption. The assumption is that gases are always at what we call standard temperature and pressure, which is really not true. Standard temperature is a specific number. What is it?
It's 0 degrees Celsius. And if you think about it, when was the last time, well, we had snow here in Houston, but when was the last time we had 0 degrees Celsius around here?
So that's like 32 Fahrenheit, right? So that's not that often. So we're all the gas numbers are making that assumption. And the pressure is at 1 atmosphere pressure, which here in Houston is probably reasonable about the pressure.
Sea level, yeah.
So sea level and 0 degrees. But we now have a situation where now what do we deal with gases that are not at 0 degrees and 1 atmosphere pressure, that at some other number?
Well, we've seen this. I just want to include this in here.
Yeah.
Whenever we're at STP, we did these calculations. We said, oh yeah, 1 mole of any gas equal to 22.4 liters. You just need to be aware that in the future, they might say, hey, this gas is at STP. They're giving you this information.
Yeah,
they're hiding it.
Yeah.
But it's there.
STP means T1 is 0 and P1 is 1 atmosphere.
And we sometimes also call it standard conditions. So just be aware that we get lazy sometimes. We don't call it STP, and they'll say, hey, we're at standard condition. You're like, wait, they've not given us enough information.
Yeah.
So today what we're going to do is we're going to talk about a snapshot in time. Remember, there's 4 variables: pressure, volume, moles, and temperature. So what we're going to do is we're going to give you 3 of those 4 variables and say,
what's the 4th?
what's the 4th?
So it's a fancy equation. It's called the ideal gas law. And I like to call it the Pivnert equation, or PV equals nRT.
Pivnert is the way we go. Yeah.
And P stands for pressure, obviously V volume, in moles.
We'll get to this guy in a second.
T is temperature, by the way, temperature always in Kelvin. R is a constant, and the constant is this. It's 0.08206 liter atmosphere over mole Kelvin.
This could probably be the ugliest unit you'll ever see, agree?
Yeah. So you got, how do you say it?
I call it latmas per molix.
Latmus per molix. There you go.
It's my little acronym or my helpful way of remembering it. Now, this is important because we've not had this R before. This is a gas constant. These are actual units: liters, atmospheres, moles, and Kelvin. And because we have this R, we now are restricted in the units that we can use.
You have to always have pressures in atmospheres, volume in liters, and temperature in Kelvin. And moles, of course, are in moles, but moles are, there's no other like similar thing for moles.
So if we give you, and we'll give you units that are not these. So instead of giving you pressure in atmospheres,
I'll give it to you in torr or something.
Torr, you can't go ahead and plug torr into here because torr and atmospheres, which are the unit in
not the same ballgame,
and they won't cancel. So when we start doing these problems, the only thing you need to be aware of is this: whenever you see a problem, they're like, here's 3 pieces of information about a gas. What's the 4th? We're using this equation. That's different than saying, here's a gas, what is the new? Anytime you see what is the new, we're going to go back to the combined gas law, which we did in the previous video. This is just, hey, here's some information, solve for additional piece of information. Probably the best way to do this is maybe to do some practice problems, yeah?
So given this question here, we've got 3.5 grams of oxygen gas, right, that takes up a volume of 42.5 milliliters at a temperature of 26 degrees Celsius. What's the pressure?
Now notice here, I like writing all the variables down on the side of the problem.
I like that. That's good.
He said grams here, and if you remember before, we never use grams in our problems, don't we? It's almost like a reflex. Moles.
Yeah.
As soon as we have grams, so this somehow or another is going to have to give us our moles because they're giving us variables, 3 of 4 variables, and they're asking us to solve for the 4th.
It's PV nRT, and we have to solve for, remember, it's got to be in liter, atmosphere, moles, and Kelvin, and actually none of these are in those. So our in is grams, so maybe we say 3.5 grams of oxygen, right, over 1. And notice, by the way, he also wrote oxygen as O2 because he's a Brinkelhoff, and it says oxygen in words here in our problem. And Mr. Dimitrich very quickly got the molar mass of oxygen, 32, because it weighs 16 or whatever. So 3.5 divided by 32, that's 0.109 moles of oxygen. So let's given this problem here, we've got 3.25 grams of oxygen gas. So notice what Mr. Dimitrich is doing here, right? He's writing down what we know, but you've said in, and grams in is moles and grams is something else.
Yeah, if you remember back when we did any problem, right? You never use grams in a problem. We always convert to moles. So this should not be foreign to us.
So we're gonna do a little conversion here, but let's keep reading the question, right?
Yeah.
And then with a volume of 6.32 liters, right? and a temperature of 27 degrees Celsius. What's the pressure?
Now, I'm gonna do this right now just so we have this as part of our numbers, but isn't R a constant as well?
Yeah.
And doesn't that determine what units we have to have?
Yeah.
Latmas per
Molic.
And that tells us what each of these units need to be in. Now, ultimately, we're solving for pressure.
Yeah, yeah. So what we have to do is we have to convert each of these into Latmers per molic, right? So let's do the moles first because it's at the top, I guess. Now you're going to do a fraction over 1, right? And then there are O2, 16 plus 16, 32 grams in a mole, right? And so I'm going to get my calculator out. I'm going to take 3.25 divided by 32, gives me 0.102 moles of oxygen. And we've got milliliters.
I accidentally wrote liters there, but milliliters.
Yeah, with 6.32 milliliters, so you've got to convert that to liters. So 6.32, and that's going to be 1,000. You have to know this, 1,000 milliliters in a liter. So we don't necessarily have to do that. If it's 6.32, it's going to be 0.00632 liters, right? And 27 degrees Celsius, that's simply just adding 273 to that. That's an easy one. That adds right up to 300 Kelvin, right? Now,
we have 4 variables.
so what's the equation we're going to use again?
Yeah, and remember, aren't they giving us 4 variables and asking to solve for a fifth?
That's right.
And that's a Pivnert world. So we're going to have this equation we have to plug into, PV equals nRT. It might have been better if I looked at the wording of this and put this right at the top of the page so we could see it. But we have it right now, and aren't we trying to solve for this?
Yeah, so P times, what's our V?
Our V right now, and
0.006, right? So P times 0.00632 equals the moles. The moles was 0.102, right? We're plugging in our numbers. Times R, which is the constant, it doesn't change, the 0.08206 number. You can also round it 0.0821, usually is just fine. And then the temperature was 300 Kelvin. Now folks, this is simple algebra, right? We've got this number equals this number times X, or P, right? And so we're gonna take these three and multiply them together, so 300 times 0.08206 times 0.102, and then divide by this number, the 006 number, 0.00632 gives me 397.
Now, the thing we have to watch here, and this is why it's important to keep our units into our problem, is units cancel out. And the units that we're working with here are these. So just take a look. Don't we have moles here and moles here? Moles cancel. Don't we have Kelvin here and Kelvin here? They cancel. And then we have liters on this side and liters on this side. When you have two things that are similar on the opposite side, they cancel. And if you take a look, the only unit that's left is ATM. And that's important because if you don't rearrange correctly, and this is why we want to encourage you to keep units in here, if you don't rearrange correctly, you're going to end up with like a unit like liters or liter atmospheres or mole Kelvin or something, and you will not have done it correctly. But this right now is the actual pressure.
And that'd be a very high pressure. But if you think about it, this is very small, 6 milliliters of gas, and you put in there 3.5 grams or 3.25 grams of oxygen. That
So
pressure
much.
inside that container, this is probably a bomb. It's probably,
This is a terror. You do not want to be anywhere near this. We feel 1 atmosphere of pressure on us right now.
almost
This-
400 is a
that
big
would be
deal.
brilliantly
Yeah.
done.
So that's how you do these problems. P equals nRT. We kind of gave you like the hardest that you could get, where you're given all kinds of things. You might be just given the P, etc. Now remember, sometimes it might say at standard condition. No, they won't say that.
They could. They absolutely could. But then you could just convert.
Then it would be a combined gas flux. It would be a comparison. Yeah, that wouldn't apply. So, anything else on P equals nRT?
No, and the reality is that if this is a plug and chug problem.
Yeah.
You have 5 variables. One they're always going to give you. So in essence, there's going to be 4 variables. They're going to give you 3 of them. Solve for the 4th. So you're just going to be on the hunt in a problem. If they ever give you just like, hey, here's 3 pieces of information. What's the 4th? This is the equation. Now, do not mix this up. If they ever say the initial blar and then the final blar, there's no place in here for an initial and a final. That's where we go back to the previous video where we're doing combined gas law. The reality on this is we just need to practice on these.
Yeah.
We could do a bunch more examples right now in the video, but we're going to do that in
You're gonna do it
class.
in class. Catch you.
See you next time.